We're going to do a little lecture on color. Color and light. Why are things colored the way they are? Like this sheet of paper here is white. These letters here that I'm drawing are black. What makes the paper white? What makes the ink black? First thing we're going to have to do is recognize that many sources, like this flashlight, they give off light. We use the term emit, or emission, to describe things that have a certain color based on what they're giving off, the light that they're giving off. So the sun gives off light, this flashlight gives off light, and you know, it looks a little bluish, but overall I think we can say that this flashlight is giving off white light. And when we describe something as giving off white light, we can actually see by using something called a diffraction grating, that's this thing here. If I place it over, look at that, if I place it over the white light, it'll actually split the white light into the colors that make up the white light. So I'm going to just stick it over here over the camera frame, and you can see when I do that, that the white light splits into the rainbow. And that's because white light gives off all the colors of light. Roy G. Biv, right? We sometimes call it that. Red, orange, yellow, green, blue, indigo, violet. All these colors, all the colors of light are given off by white light. And objects that are opaque, that means light cannot pass through the object, like this piece of paper. Objects that are opaque, they get their color based on the colors of light that get reflected off of the opaque surface. So for example, this particular white sheet of paper, when I shine this white light on it, all the colors of light, the whole rainbow, bounce off of this and into my eye. And because all the colors together make up white light, when all those colors collectively hit my eye, I see this, all those colors together as white. So an opaque object has a particular color based on the colors of light, or the color of light that reflects or bounces off the surface. So I'm going to show you a couple of experiments here that demonstrate this. So I'm going to take a red piece of foam and a green piece of foam, and I'm going to take a green laser. There, let me take my green laser. My green laser emits green light. And I can see, boy, that's reflecting off that white sheet of paper very well, and that'd be expected. I expect all colors of light to reflect quite well off of a white surface. Let's see how this green laser reflects off of a green piece of foam and a red piece of foam. Well, that's a big difference. Do you see that the green light, the laser's brighter when I shine it on the green surface rather than on the red surface? That's because this object is green, because green light reflects off it very well, bounces off of the green surface and into my eye. The red object, the green light doesn't bounce off of this very well, and in fact a lot of it gets absorbed. So a lot of the light ends up getting absorbed by the sheet of paper. It doesn't get reflected. Let's do the same experiment, but we're going to do it, in this case, we're going to do it with a black sheet of foam and a white sheet of foam. So we'll repeat the experiment, and we see, oh my goodness, it's very bright on the white sheet, and on the black sheet, not so much, right? And that's because an opaque black object, the light that hits it, almost none of it gets reflected, and so it looks dark because there's no light coming off of it. A white object, all the colors that strike a white object reflect off, and when all the colors get added together, it appears white. So an opaque object has the color that it does based off the colors that reflect off of the opaque surface. Now we're going to talk about objects that are transparent, like these filters here. And color works a little bit differently with transparent objects. In this case, the color of the object, of the transparent object, happens to be the color that transmits through the transparent object. So here, I'm going to turn this flashlight on, and we're going to go ahead and place this red filter over the camera lens. And when I do that, I only really see red light tending to get through the flashlight. So what happens is when, this white light source, it's giving off all the colors, it's giving off RoyGB, the color that tends to get through the red filter is just the red light. That's why this looks red, right? All the other colors are tending to get absorbed. The red light goes through. Let's try the same thing with this green filter. Of course, it's going to look green, and that's because as this flashlight gives off all the colors of light, it gives off RoyGB, green transmits through the green filter. So the green light goes through and into the camera, and so that's why it looks green. All the other colors tend to get absorbed. Let's try this with the laser. So see if you can guess. I'm going to take this laser, and I'm going to shine it through both the red filters and the green filters. Let's see what happens here if I do this. So I'm going to take the green laser, and I'm going to place the green filter over it. So you can see that I place the green filter over the green laser, and the green light transmits through the green filter. That's why this looks green, because it lets green light through. Let's try the same thing with the red filters. So I got the green laser on. I'm going to take the red filters. Holy cow, look at that. That's crazy. That is amazing. So you can see that the green light does not, well, I mean, a little bit of it does, but that's because this is a laser. I mean, it's just like a huge beam. But most of that green light ends up getting absorbed by the red filter, because a red filter doesn't allow green light through, it lets red light through. That's why this appears to be red, because it's red light that it allows through. And there's a rule you can use. This is not a law. It's not, it doesn't work all the time. It's just like a guide. It's called the color wheel. And so I'm going to take a wheel and I'm going to separate it like this. And around the wheel, I'm going to write red, orange, yellow, green, blue, and violet. And the way this works is if, something that's transparent appears red, then it absorbs the opposite color very well. So a red filter is going to absorb green light very well. On the other hand, a green filter, that's going to be able to absorb red light really well. Let me get out a red LED and see if I can't show you this. Okay, here's my red LED. Red LED, this is green. The opposite of green is red, so this, oh, look at that. Wow, that really absorbs that red light really well, doesn't it? And so this color wheel helps us understand, what colors a transparent object is going to absorb. So if something's green, it's going to absorb red light really well. If something is red, it's going to tend to absorb green light really well. If something's blue, it's going to tend to absorb orange light really well. If something's orange, it's going to absorb blue light really well. If something's violet, it's going to absorb yellow light really well. And if something's yellow, it's going to absorb violet light really well. Again, this isn't like a law, it's just a guide that helps you understand color. A couple more things I want to cover here, and this has to do with wavelengths of light. So wavelengths of light. This is the symbol for wavelength. If we're looking at the rainbow, so we're looking at red, orange, yellow, green, blue, and violet light, it turns out that the red light is going to have the longest wavelength of the colors of light you can see. Of course, there's longer waves in this direction that we cannot see, and there's shorter waves in this direction that we can't see. But violet light, that's going to have the shortest wavelength of all the colors of light that you can see. And from our equation, c, speed of light, is the frequency times the wavelength. If we divide both sides of this by a wavelength, we see that frequency is the speed of light divided by the wavelength. This means that there's an inverse relationship between frequency and wavelength. So as wavelength gets bigger, we got a bigger number on the denominator. That's long. If I'm dividing by a bigger number, the frequency is going to get lower. So these have low frequency. And of the colors of light, red has the lowest frequency. On the other hand, if it's a short wavelength like violet light, if I'm going to divide by a small number, that's going to give me a big frequency. So violet light has the highest frequency of all the colors of light that we can see. There's higher frequency wavelength in this direction. There's lower frequency wavelength in this direction. But nevertheless, that's how it works. And I want to show you a type of light. Let me see if I can put this on here. I think I may have mentioned this before. I'm going to show you a type of light that you cannot see that has a longer wavelength than red. Let's see if I can. Oh, there it was. Watch that little button. There's a little thing right there. See it? This camera here can pick up that wavelength of light, which is called infrared. Infrared light. It's got a longer wavelength than red light, so it's going to have a lower frequency than red light. And so my eyes, I can't see it. I mean, this is from your face recognition software. So this little light that you might see sometimes, it's a beam of infrared light that scans out and it looks at your face. I don't know how it does that, but somehow it can recognize you. And we can't see it with our eyes, but this camera can pick up that infrared light, which I think is pretty interesting. Okay, so you can play around with infrared light using your cell phone. I'm going to show you how to do that. First, you're going to want to go into your camera, and you're going to want to go to selfie mode. Hello. Okay, so selfie mode on your camera can actually pick up infrared light. So I've got my TV remote here, and when I push the button on my TV remote, I hope this works. When I push the button on my TV remote, I'm pushing power. Oh, look at that. You can see it, right? This camera here can pick up infrared light, but your cell phone camera can do it too. So I'm going to put this in the way. Oh, I gotta go selfie mode. How am I going to do this? Oh, here it is. That's how I want to do it. Okay, sorry. So there we go. I got my selfie mode here. You see that? No, hold on. I got to get this right so you can see it. There it is. Got it. So I've got selfie mode on my cell phone, and I'm pushing the power button on my TV remote, and there's an infrared beam that comes out of my TV remote when I push on it. And that infrared beam, I can't see it with my eyes, but this camera can pick up. And the selfie mode on your camera, that can pick it up too. Oh, let's try one more time. Selfie mode camera, infrared light, come on, let's get this. There it is. So you can try that. One more thing I want to cover. Light is sometimes described as a particle. When we talk about light being a particle, we call it a photon. That's a particle of light. So you can think of it as a little tiny hard BB. It turns out that the energy of a photon is proportional to its frequency. So what that means, the energy of a photon goes up when the frequency goes up. And because frequency and wavelength are inversely related, the energy of a photon goes down as its wavelength goes up. So There's an inverse relationship between energy and wavelength. There's a direct relationship between energy and frequency of photons. And that covers all that we need to cover about light.